Okay, today we're going to look at some typical problems for Chapter 5. The first part will involve circular motion, the next will involve gravity. So first of all, we have the radius of the Earth around the Sun is 1.5 times 10 to the 8 kilometers, and the Earth travels this orbit in 1 year, which is 365 days. We want to know what's the magnitude of the orbital velocity of the Earth in meters per second, and what's the radial acceleration of the Earth towards the Sun in meters per second squared. Okay, so we've got two equations basically for circular motion. One is that the speed is equal to the circumference of the orbit divided by the time it takes to go around. And the second equation is that the acceleration towards the center of a circle is v squared over r. So I think we're going to use equation 1 to do A and equation 2 to do B. So first of all, part A, what's the magnitude of the orbital velocity? So I just want v is 2 pi r over t. So I've got 2 pi, the radius is 1.5 times 10 to the 8 kilometers. And I'm going to have to put that into meters. Okay, so radius 1.5 times 10 to the 8 kilometers. And there's 1,000 kilometers, sorry, 1,000 meters in 1 kilometer. So that gives me 1.50 times 10 to the 11 meters. So put 1.50 times 10 to the 11 on top. On the bottom, I've got to put the period. Now, the period is in days. I need to get this in seconds. Okay, so I've got 365 days. And convert how many seconds in a day. I'm going to do a shortcut. There's 86,400 seconds in 1 day. So if I do that calculation, 365 times 86,400, I get 31536,000 seconds, which is 3.1536 times 10 to the 7 seconds. So now I just do that calculation. Okay, so V is equal to 2 times pi times 1.5 times 10 to the 11 divided by 3.1536 times 10 to the 7, and I get 29,886 meters per second. I've got 3 sig figs, so that's 2.99 times 10 to the 4 meters per second. Okay, part B, what's the radial acceleration? Well, now I've got my v, so I can just put in v squared over r. So I've got, now let me write it down. Remember, keep all your sig figs till the end. 29,886 squared divided by the radius, 1.50 times 10 to the 11 meters. Plug that in your calculator. And you get a small acceleration point, 0.00595 meters per second square. Okay, so pretty easy. We will only have 2 different equations for circular motion, one for V and one for A. For Chapter 5.
Now I have a small car with a mass of 0.8 kilograms. It travels at a constant speed on the inside of a track that's a vertical circle with a radius of 5.00 meters. So let's draw what that means. This is something like your little dinky cars, and you've got your car going around on the inside of the track. Okay, we're told it's a circle with a radius of 5 meters, so the radius here is 5.00 meters. And we're told that at the top of the track, so that's when the car is upside down here at the top, we have a normal force of 6.00 newtons. We want to know what's the normal force at the bottom of the track. Okay, so let's think about what's happening. So let's draw a free body diagram of the car when it's at the top of the racetrack. So when the car is at the top of the racetrack, what forces are acting on it? Well, we've got gravity, acting down. We've got the normal force, which is the force of the track pushing on the car, so that's also going to be down. We don't have any tension, there's no string attached. We don't have any friction because we're not told there's any friction on the track. So those are the only two forces that we have. Okay, so I've got two forces both acting downwards. The force of gravity is mg, and my normal force, I'm told, is 6.00 newtons. I can calculate what my force of gravity is because I know the mass, 0.800 times 9.8 is 7.84 newtons. So I've got my total force is 7.84 plus 6.00 newtons downward, so it's 13.84 newtons. Okay. What else do I know? Well, I know that that has to be equal to mv squared over r if the thing is moving in a circle. So I could use this to get my speed. I know my mass, I know the radius. So why don't we rearrange it and do that, and then we'll figure out why we want to do that. Alright, so I've got 13.84 newtons is equal to mv squared over r. I want to solve for v. So rearrange it. I've got 13.84 times r divided by m is equal to v squared. So my speed is equal to the square root of 13.84 times the radius, which is 5, divided by the mass, which is 0.8. So I'll put that in the calculator. 13.84 times 5 divided by 0.8 equals, and the square root, I get my speed is 9.30 meters per second. Okay, so now we know everything about what's happening at the top of the rack. What's happening at the bottom? Let's draw another free body diagram. So now at the bottom, I've got my weight, which is downwards. I've got my normal force, which is upwards. My weight is still going to be 7.84 newtons. My normal force is going to be different, and they want me to find what it is. And again, those are the only two forces we have. So now I've got my total force is equal to my normal force minus 7.84. Okay, and what is that force going to be? Well, it's got to be equal to mv squared over r towards the center. And mv squared over r, that's going to be the same as up at the top because I need to still have the same speed because I'm told it's a constant speed. I've got the same radius, I've got the same mass. So this total force has to be equal to 13.84 newtons. So you can see we actually didn't need to solve it for v. So my normal force then is equal to 13.84 plus 7.84, which is 21.68 newtons. Okay, so that means at the bottom of the track you feel heavier than you do at the top of the track. And if you've ever been on a roller coaster or something that does a loop-de-loop, you'll know that, yes, on the top of the track you almost feel like you're falling out of the car. That's because the normal force between you and the car is very small. And at the bottom you feel really heavy. You feel like there's a lot of force pushing on you. Now let's do a gravity problem. I want to find the magnitude and the direction of the net gravitational force on mass A, this one here, due to masses B and mass C in this figure. Each of the masses has a mass of 2 kilograms, and we're told A and C are 10 centimeters apart, and A and B are 40 centimeters apart. So we know the gravitational force from Newton's law is G m1 m2 over the distance squared. So I can figure out the force between A and B is G times the mass of A times the mass of B divided by the distance between A and B squared. And the force between A and C is G times mass A, mass C, divided by the distance between A and C squared. So let's put in our numbers. G, big G, 6.67 times 10 to the negative 11. All the masses are 2 kilograms, so I'm going to have 2 times 2 on top. And on the bottom, I need to put in my distances. So the distance between A and B
is this 40 centimeters, which is 0.40 meters. Remember, we've got to put everything into standard SI units. Let's square that. And the distance between A and C is 10 centimeters, which is 0.10 meters. So let's plug those guys into the calculator and figure out what we have. So 6.67 times 10 to the minus 11 times 2 times 2 is 4, divided by 0.4 squared, and I get 1.67 times 10 to the negative 9 newtons. If I do it for the other one, 6.67 times 10 to the minus 11 times 4 divided by 0.1 squared, I get 26.68 times 10 to the negative 9 newtons. And if I look up here, see, I wrote that down wrong. I said 9 and I wrote down 19. That's times 10 to the minus 9. Okay, so what's my total force? Well, forces are vectors, so we have to add them like vectors. This is a one-dimensional problem, so let's look at the force on A due to B. Well, it's an attractive force. It's getting attracted towards B, so that's over to the right. The force on A due to C is towards the left, so I'm obviously going to subtract those guys from each other. And you can see, as we'd expect, the force on A due to C is a lot bigger than the force on A due to B because they're a lot further apart. B is 4 times further away, and so remember the force goes as 1 over the distance squared. So I'd expect if it's 4 times further away, the force should be 1/16 as big. If you look at that, that looks about right. Okay, so this is a one-dimensional problem. So if I want to get my total force, it's going to just be the force of A on B to the right, 1.67 times 10 to the minus 9, minus the force on A due to C to the left. I'm using the standard notation where to the right is positive and to the left is negative. And I get negative 25.01 times 10 to the minus 9 newtons. So the magnitude of the force is 25.01 times 10 to the minus 9 newtons. And I've got 2 sig figs, it looks like, so 25 times 10 to the minus 9 newtons. And the direction, I've got a negative sign there for a one-dimensional problem, so it's to the left. So the net force is towards C from A. Okay, last problem. For a satellite to be in a circular orbit 780 kilometers above the surface of the Earth, what orbital speed must it be given, and what's the period of the orbit? Okay, so let's draw a picture of what we have. So we've got the Earth, and we've got our satellite, which is going around in a circle. We're told that our satellite is 780 kilometers above the surface of the Earth. The radius of the satellite's orbit is the distance from the very center of the Earth up to where the satellite is, so we have to add on the radius of the Earth in there. Okay, so what's our equations? Well, we've got a gravitational attraction between the mass of the satellite and the mass of the Earth. We've got the force has to be equal to mv squared over r, and the mass is going to be the mass of the satellite, since that's the thing that's going around in the circle. And we want to know what's the orbital speed and what's the period. So first of all, let's find the orbital speed. So in order for it to go in a circle, these two forces must be equal to each other. So I've got g, mass of the satellite, mass of the Earth, over the radius squared is equal to the mass of the satellite times v squared over r. The mass of the satellite cancels out. I want to find v, so let's rearrange this. V squared is equal to g me times r over r squared, so that's g me over r. So the orbital speed is equal to the square root of that, g times the mass of the Earth divided by r. And we can look up the mass of the Earth in the index at the back of the book or just Google it. I get 5.98 times 10 to the 24 kilograms. The radius of the Earth is 6.378 times 10 to the 3 kilometers, which is 6.378 times 10 to the 6 meters. And of course, we know that the radius of the Earth varies depending on whether you're over the ocean or over a mountain, but this is just an average. Okay, so we know the mass of the Earth, we know G, we've got to figure out what R is. So R is equal to 780 kilometers, so 780 times 10 to the 3 meters, plus the radius of the Earth, 6.378 times 10 to the 6 meters, and I get 7.158 times 10 to the 6 meters is the radius of the orbit. So now just plugging that in, I've got 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, divide by the radius, 7.158 times 10 to the 6, and I get an orbital speed of 7,465 meters per second for that satellite. Okay, so that's the orbital speed. What's the period of the orbit? Now we go back to what we had for our very first problem for this chapter. Remember, we say that V is equal to the circumference of the orbit divided by the period. So that means the period is equal to 2 pi r over V. Now, a lot of people mess up when they change this around. They say that it's V over 2 pi r. Make sure you understand the algebra on how to do this. Okay, so now it's just plugging in the numbers. So put in our radius, 7.158 times 10 to the 6 meters. Our speed, which we just found, 7,465 meters per second. And we get a period of 6,024.8 seconds. And we know that there's 3,600 seconds in an hour, and this comes out to 1 2/3 hours. Okay, so this satellite's going to go whizzing around the Earth